Welcome, kids, to stoichiometry. Stoichiometry is a very hard word, but the math is pretty easy. And I'm good at this, and you're smart, so this should not be too tough. Stoichiometry, we're going to be using ratios of balanced chemical equations, and we're going to manipulate these mathematically. We're going to have fun. Honestly, I'm going to have fun. You need a calculator, reference table, and your notes, and better get your thinking caps on. So question number one, what the heck is stoichiometry? Stoichiometry is math that follows the law of conservation of matter that starts with a balanced chemical equation. And from the balanced chemical equation, we can really jazz it up. But obviously we have to write a balanced chemical equation with the proper formulas in the lowest John Dalton ratio, right? Simple whole number ratios. If you can't do that, all this stoichiometry mathematics is just going to be pressing buttons on the calculator. So try your best to get the formulas correct. Here we go. So one of my favorite things to eat is called brownies. Brownies are made like this. You get a box of brownie mix. You mix 3 eggs in it with a cup of water and a half a cup of oil. You stir it up and you bake it. Depends on what kind of person you are. That makes 1 big brownie, or maybe 2 pretty good sized brownies, or I guess if you follow the directions, it makes 12 small brownies. But that's the recipe. Box of mix, 3 eggs, cup of water, half a cup of oil. What if we want to make a double batch? A double batch, not one. You're going to have a friend over, so you're going to make a double batch. What do you need? Well, you need 2 boxes, you need 6 eggs, you need 2 cups of water, and you need a whole cup of oil. See how I did that? I doubled it in my head. Well, the recipe for brownies is kind of like a balanced chemical equation. It's even in a ratio, simple whole number ratio, 1 to 3 to 1 to a half. I guess it's not a whole number ratio, but it's a simple recipe. But if I double it, I double everything and I get a double batch, right? What if I ask you this question though? How much oil do you need if you want to make 3.75 batches? That's a dumb number, right? This is a chemistry class. You got a calculator. Let me show you how to do that. Don't get all excited. Don't even try it. Just think about this. 1 batch requires a half a cup of oil. 2 batches requires 2 cups. When it's complicated, you got to do some math. We'll make a ratio. 1 batch requires half a cup of oil. 3.75 batches requires X cups of oil. How do you solve this equality? You cross multiply. 1 batch times X. 1X equals whatever 1/2 times 3.75 is, 1.875 cups of oil. That we could figure that out. That is sort of stoichiometry. Now, we don't really do stoichiometry on brownie mixes, right? You just make 1 mix at a time, you eat it, you make another mix if you're hungry. But stoichiometry, we take any balanced chemical equation and we do some math on it. And that's all there is. Ready? Let's do some chemistry now. This is a nice, simple, balanced chemical equation. Aluminum and oxygen synthesize into something called aluminum oxide. Aluminum's a metal, it's a solid. Oxygen's a gas, it's a gas. And aluminum oxide's an ionic compound. It's a solid, unless it's thousands of degrees centigrade, which it's not. What is called the mole ratio for this? Because what does this say? This says 4 atoms of aluminum plus 3 molecules of oxygen makes 2 formula units of aluminum oxide. But as it turns out, it also is 4 moles of aluminum plus 3 moles of oxygen makes 2 moles of aluminum oxide. The mole ratio is 4 to 3 to 2. Now this is important. It could be 4 Al atoms plus 3 molecules of oxygen makes 2 formula units. But if we multiplied it, say by Avogadro's number, each part, and made it grow, we could say that 4 moles of aluminum require 3 moles of oxygen to make 2 moles of aluminum oxide. Every balanced chemical equation, the ratio is atoms to atoms or atoms to molecules. It's also moles to moles. So this is a 4 to 3 to 2 mole ratio. Now use your brain. 4 to 3 to 2, that's the ratio. What if we use up 8 moles of aluminum? how much oxygen would you need? 4 moles requires 3 moles. 4 moles of aluminum requires 3 moles of oxygen. 8 moles of aluminum would require 6 moles. How would we do that? Well, it's 4 moles of aluminum to 3 moles of oxygen is proportional to 8 moles of aluminum over X moles of oxygen. How do you do this? You cross multiply. 4X equals 24. Divide both sides by 4. X equals 6. 6 what? Look where the X is, right in the middle of the table. X is moles of oxygen, so it's 6 moles of oxygen. This is kind of like stoichiometry too. Same equation. What if you only use up 1 mole of aluminum? How many moles of aluminum oxide, right? 4 moles of aluminum, you need 3 moles of oxygen. What if you only had 1 mole? Ooh, we got to do some math. Oh, you know what? It's not 2 oxygen. This is 4 moles of aluminum makes 2 moles of aluminum oxide. Forgive me. So in this ratio, we have 4 moles of aluminum is proportional to 2 moles of aluminum oxide. But what if we only want to use 1 mole of aluminum? How many moles of aluminum oxide form X? And we set up a ratio, we cross multiply. 4X equals 2, X equals 1/2 mole of aluminum oxide. This is very simple mathematical games we could play with the balanced chemical equation. Very simple stoichiometry. It's going to get not harder, just a little fancier. Now, take out table H. Table H, which I have right here, has a lot of space at the bottom. Remember this big, beautiful graph, and you have all this space? You drew your mole ratio right over here. Well, if you didn't, you're going to do it now. But let's see what we're going to do at the bottom of this. This new map, the stoichiometry mole map, is going to be the guide for all stoichiometry forever. Every stoichiometry problem in the universe. Just like the mole map was the map for all mole problems, this new map that we're going to add to is going to be the map for all stoichiometry problems. Now, this is what we used to have, the blue one. We used to have the blue mole map. Now we're going to have a slightly orange one to the side, and we're going to connect only the 2 middle islands, Mole Island to Mole Island 2. So you have the same island names. We got Mole Island 1 and Mole Island 2. Up top, there's Volume Island and Volume Island 2. Bottom left, we got Particle Island, and we have Particle Island 2. On the bottom right, we have the blue Mass Island, then we got Mass Island 2. And they're only connected by the mole ratio tunnel. It's a whole new set of islands, so a lot more chemists and their kids can go on vacation and not get in trouble. There's still a mole shark up there in a corner that's going to eat you if you get off the bridges. We got bridges on the left and bridges on the right, and it's the same toll. Make sure you write this very, very neatly down here. Make sure you draw the shark so you remember not to get eaten by the shark. This is stoichiometry. So what we could do is take any balanced equation, and the moles of one part are in proportion to the moles of the other. We just did 2 problems. The moles of aluminum to the moles of oxygen, and then we did the moles of aluminum to the moles of aluminum oxide. The moles are in proportion. But what this map is going to let us do is let us say things like, what if we had 53 grams of aluminum? How many liters of oxygen would it be? Now, the moles are at a 4:3 ratio, 4 moles of aluminum to 3 moles of oxygen. But now we can fancy it up. We can say, wait a second, what if we had 53 grams of aluminum? How many liters of oxygen? So we got to do mole math on both ends of this and do a ratio in the middle. So the biggest problems we're going to do are going to be 3 steps, but it's going to be fun. Honestly, it's not going to be hard. It's not. You could hit pause. I'm going to keep going. If you got to keep drawing this picture, hit pause and then catch up to me. I'm going to keep going. Look at this problem. You're going to react 216.5 grams of aluminum. How many liters of oxygen is it going to be needed? How many liters of oxygen will be necessary to complete this reaction? Now let's think about this. This is what we got. Can you see my little picture here? We're starting out here with the mass of aluminum, and we want to know the volume. We're going from this island over here to this island over here. The only way to get there is to take the mass of aluminum and convert it into moles of aluminum. Grams to moles, we know how to do that. Then we're going to do the ratio, the proportion of moles of aluminum in proportion to moles of oxygen. That's in 4 moles of aluminum to 3 moles. And then once we know how many moles of oxygen, we're going to convert that into liters up here. This is the biggest possible stoichiometry math problem. 3 steps. It can't get harder than this. So we'll go slow. We'll get through this, and you'll be like, wow, can't get any worse than that. Here we go. This is how you do it. Step number 1. We have to convert the grams of aluminum into moles. How do we do that? Well, we start with our starting point, 216.5 grams of aluminum over 1, and then we need to get the periodic table out. I'm getting mine out right now, and we have to get the molar mass of aluminum. How do you do that? You put your finger in this box for aluminum, and you see that when we round it to the nearest whole number, read my lips, no decimals, 27 grams per mole. The grams on the top, the grams on the bottom cancel, and we do the math. This is a division problem, really. 216.5 divided by 27 with 4 significant figures. That many grams of aluminum is 8.019 moles of aluminum. That's good. That's first step. We switched the mass into moles for aluminum. Now, the second step, we got to compare the moles of aluminum, compare them to the required moles of oxygen. Now, this is how we do it. This is so important right here. Stop and pay attention. We're going to write the letters MR. That stands for the mole ratio. Now, there's a lot of different ratios here. Which one are we looking at? We're looking at the ratio between aluminum and oxygen. So I'm going to write Al over O2 because we're looking at the ratio of aluminum to the ratio of oxygen, which is in a 4 moles to 3 moles ratio. Look at the balanced chemical equation. It's 4 Als plus 3 O2s. So it's a 4 to 3 ratio. Now, in this math problem, because it's chemistry, it's a stoichiometry, it's not just 4 moles to 3. We have this crazy number. We don't have 4 moles. We have 8.019 moles. Well, if 4 moles is proportional to 3 moles aluminum to oxygen, then there must be a mathematical equivalent, 8.019 moles of aluminum to X moles of oxygen. This is an equality. It's a proportion. And we solve it by cross multiplying. It's going to be 4X equals 24 point something, right? 24.057. We're going to divide both sides by 4, and with 4 significant figures, the amount of oxygen required to react with that many moles of aluminum is 6.014 moles of aluminum. We're going to stop. We're going to slow down. In a simple balanced equation, it takes 4 moles of aluminum. It takes 3 moles of oxygen to react with that. But this is a math problem. We don't have 4 moles of aluminum. We happen to have 216.5 grams, which is a wacky number. We convert that number into moles. And now we have to remember it's in a 4 to 3 ratio, but we have 8.019 moles to X. What is X? X would be how many moles of oxygen would be required to react with this much aluminum. Are we done? No, we're not done. 3 steps. We went from grams of aluminum to moles of aluminum. Then we compared the moles of aluminum to proportional amount of oxygen. Now we have to take the moles of oxygen, which is right there, and we have to convert it into liters by using that equality that you already know. 1 mole is equal to 22.4 liters. So here we go on the bottom. Our newest starting point, 6.014 moles of oxygen over 1, and we're going to multiply it by this conversion factor, 22.4 liters of oxygen is a mole. The moles cancel out, and the answer comes out with 4 significant figures to this number, 134.7 liters of oxygen. Let's just stop for a second and try to figure out what the heck just happened. First of all, number one, it's not going to get any harder than this. Number two, we have a red balanced chemical equation. 4 aluminums and 3 oxygens makes 2 aluminum oxides. In stoichiometry, you can take any 2 parts of an equation. We're talking about aluminum and oxygen. We're not even talking about aluminum oxide. That'll take care of itself. 4 moles of aluminum need 3 moles of oxygen. But it's a math problem. We don't have 4 moles, we have grams. So we have to convert grams into moles first. Then we know the mole ratio of aluminum to oxygen. It's in the balanced equation, it's 4:3. Then we take the moles of aluminum that we have, 8.019, and try to figure out what's the proportional amount of oxygen that we need. And that's the number, 6.014. So that's how many moles of oxygen are required. But the question doesn't say how many moles. The question is a pain in the neck. The question says how many liters. So you have to convert the moles of oxygen into liters. In a balanced chemical equation, there's a mole ratio, but you know how to convert moles into atoms or molecules or liters or grams or back. So stoichiometry is taking a balanced chemical equation and doing some fancy math on it. All right. There's 3 levels of questions. This is a really easy slide here for you. The hardest questions we just did, there are 3 steps. You go from one island to moles, moles to moles 2, and then from moles 2 to a different island. Those are the biggest problems. Can't get any bigger. There's none bigger in the whole universe. Sometimes there's only a 2-step problem. You start on moles, and then you go to a different island on the other side. Or you start somewhere and you only go to moles 2. It's 2 steps only. And every once in a while, we can go from moles to moles. It's just a proportion for 1 step. Okay? Stoichiometry allows you to use a balanced chemical equation to figure out all kinds of fancy mathematics. It's easy. You already learned about balancing equations. You already learned about moles. The only thing new is that we're gonna include this little proportion called the mole ratio between one part of the equation and the other. That's all you got so far. All right, we're done with this whole first class. How's that? Take a break. All right.